Welcome to our first webinar of the spring for the USACM Energy and Earth Systems Technical Thrust Area. So I wanted to just say a little bit about the technical thrust area before we get into the seminar. For those who aren't familiar with us, so USACM is the U.S. Association for Computational Mechanics. We're one of the newest technical thrust areas. We've been around for a couple of years, and I'm Irina Tazar, I'm the chair. And so we cover a variety of topics, and so some of them are listed here. So climate and earth system modeling, climate couplings, geomechanics, wind, solar, nuclear energy, carbon sequestration, capture and storage, oil, gas recovery. And I would encourage you to join officially, which you could do through the USACM website. So if you're a member of USACM, joining the TTA is free. If you're not a member, if you attend the USACM conferences, you get discounts on attendance. So there's that benefit for joining. And if you're unable to join officially, we do have a LinkedIn site where I post announcements that you can follow for free if you're on LinkedIn. And so, oops, why is this not advancing? Here we go. So just a quick kind of prequel here. I finally have all the webinar speakers lined up for the spring. So they will cover a variety of different topics. So we have Rebecca Ginny from UCSD on February 24th talking about climate model calibration. We have Professor Hadi Hajabegi from TU Delft in the Netherlands on the 31st of March, talking about subsurface storage. We have Professor Mariana Mayaru from Columbia University talking about wind turbine blade manufacturing on April 21st. And then finally on June 2nd, we will have Dr. Shamina Hossein McKenzie from Sandia National Labs give a talk on some of her electric grid work. So really a diverse set of topics this time around. So let me stop sharing here, and I'll let Stefan go ahead and share his slides while I'm introducing him. So today's speaker, it's really my pleasure to introduce him. I'm quite excited about this talk. So it's Dr. Stefan Henneking, who is a research associate at the Odin Institute for Computational Engineering and Sciences at UT Austin. His research focuses on theory and HPC-enabled computational methods for large-scale Bayesian inversion-based digital twins, with a particular emphasis on wave propagation problems, which include applications in acoustic sensing, fiber optics, and the topic you'll hear today, which is tsunami early warning. Stefan has a Bachelor of Science in Computational Engineering from FAU Erlangen-Nuremberg, a Master of Science in Computational Science and Engineering from Georgia Tech, and a Master of Science and a PhD in Computational Science, Engineering, and Mathematics from UT Austin. And as the title suggests, he is a recipient of the 2025 ACM Gordon Bell Prize, and that's what he'll be talking about today. So with that, I'll hand it over to Stefan to give his talk.
All right. Thank you, Irina. Thanks so much for the introduction. Thank you for inviting me to present the talk, and thank you everybody for joining. So I'm gonna use the next 45 minutes to give you an overview of the work we've done for this Gordon Bell paper, but also some of the theory behind it, a little bit more length than what I was able to present with Omar and Shriram at Supercomputing. And this effort for the Gordon Bell paper specifically involved a whole team of collaborators here. So in addition to me, Shriram, and Omar, we also had Melinda from UT Austin join the effort, Alice Gabriel from Scripps at UC San Diego, as well as Veselin, John, and Sanyo, who all work for the MFEM team at Livermore Labs. Now, here's the paper that we presented at the Supercomputing conference. And just because I'm going to be talking quite a bit about things that we presented in this paper, there's going to be also a heavy focus on computations, on algorithms, computational results during some parts of the talk. So I hope that is something you're interested in. Now, just to set the stage, so what are we motivated by for our work here? And this is where we really started a few years ago. We were looking at the Cascadia subduction zone, which many of you are probably familiar with. It's the large subduction zone of the northwest coast of the US and Canada, of the Pacific Northwest coast. It's depicted here. And so what's happening here is that along this long red line that's marked here in the plot, there is the subduction zone between the Juan de Fuca plate in the west and the American plate in the east. And the Juan de Fuca plate is pushing underneath the American plate, is moving eastwards. And for a long time, it was thought that these plates are freely sliding alongside each other. But then sometime in the 1980s or so, researchers found that those two plates are actually locked in a large area. This area is roughly shaded here in red. And so because they are locked, as the Juan de Fuca plate is pushing, this locking mechanism causes the American plate to be slowly lifting up over many years, decades, centuries. At some point, the friction forces that hold these two plates together will be overcome by the strains, and the American plate is going to snap back, and this will cause a big rupture event, an earthquake event, potentially a megathrust earthquake, that will also displace a really large quantity of water upward in the ocean, which then propagates onto the shore eastward to the US and Canada, as well as west, eventually reaching Japan. What makes this particularly hazardous here in this case is the fact that the subduction zone is located so close to the shoreline. So when the earthquake rupture happens here, from initiation to the tsunami reaching the shore, for some coastal communities, this might be as sort of a time window as about 15 minutes or so. So very little time for early warning and evacuation. Now, again, if you're familiar, you've probably seen these things, but it's actually quite fitting that I'm giving this talk today, because it was exactly today, 326 years ago, that people in Japan and coastal villages in Japan observed or were hit by what they called then an orphan tsunami. So a tsunami that arrived in Japan that wasn't explainable through an earthquake that was felt. And this tsunami wasn't really explained where it happened until much later. In the 1990s, there was a big storm system in the Pacific Northwest. And what it uncovered is these, what we call ghost forests. This here is an example on the left of Nesquehoin, which is in Oregon, on the Oregon coast. But you'll find these along the Pacific Northwest coast in many places. And these are old coastal forests that were destroyed by a tsunami wave. And this was then dated in the 1990s, and it was determined that this had happened in January of 1700. So January 26th of 1700 is when the rupture happened here. And there's other evidence that we have gathered since then in this community. And with paleoseismology, we're able to then determine that this subduction zone, this Cascadia subduction zone, has had major ruptures in the past every 300 to 500 years or so. And the current estimates are that there's a large likelihood, about a 1 in 3 probability for a major rupture event in the next 50 years, which could be potentially devastating for the Pacific Northwest coast. Now, in terms of instrumentation for early warning, there really is very limited instrumentation in place at this point in terms of offshore instrumentation. There is a number of different proposals that people have come up with. One of them is shown here, that was published in 2019. So the idea is that in order to provide real-time data that can be used for early warning purposes, that we would install seafloor pressure sensors, stations on the sea bottom, which are connected by fiber optic cable, a seafloor cable, which then provide, when the rupture happens, real-time data that can be used for early warning purposes. And this is really what we assume or envision, and what the assumption that we build our model on is that at some point in the future, there will be more data available than what is today, which is today we have a very sparse network of sensors offshore only. Now, the current methodology for forecasting, so when the earthquake happens, primarily using information from seismometers, we characterize the earthquake source as the first thing. So this is done very quickly usually, and those estimates are being updated in time. And then for tsunami propagation, most models are using the shallow water equations, and the shallow water equations are an efficient model for just propagating a tsunami wave forward. However, it's an incompressible model. So if you think about observing the pressure field in the vicinity of an earthquake, so the ground is shaking, you have these hydroacoustic waves, the ocean acoustic waves that are propagating. And when you look at the pressure transients that are then recorded by these sensors, and we have this from past earthquakes, primarily in Japan, but some other places as well, you'll see these really high magnitude hydroacoustic waves that are propagating. And so this is something, using these pressure fields is something that wouldn't be possible with the shallow water equations because they don't have representation in the model from those. So our idea is to want to use this near field pressure data that is recorded near where the subduction zone is, and from that infer the ground motion, so the shaking of the seafloor, the seafloor velocity, if you will, that causes this pressure data to occur. And then also from this inference of seafloor motion to then forecast the tsunami wave heights at coastal locations or close to shore for tsunami early warning. We are going to be using high fidelity PDE models for this. So as you will see, I'm using an acoustic gravity wave propagation model that couples the ocean acoustic waves with the surface gravity or tsunami wave. We'll do this in the Bayesian framework so that we can quantify uncertainties. This is really essential in the context of early warning to be able to specify the confidence of our forecasts. We need to do this in real time. So this, of course, is always problem dependent what real time means. But in our case, really, given this proximity to the shoreline, once the data is acquired, we really want to be able to solve this inverse problem in a matter of seconds to provide early warning. Now, by using these methods, and especially high fidelity physics models, we potentially could do much more accurate forecasting than what is available today. Now, all of these are big challenges taken together. It's feeling like this might be an intractable problem, especially if you take into consideration that this inverse problem will have to infer the seafloor motion for this vast area of ocean. And as it will turn out, the spatiotemporal field describing the seafloor motion has about 1 billion parameters or so. The forward model itself also has many billions of degrees of freedom. And that's because we have to describe the acoustic wave that propagate in the ocean domain. So that's kind of the framework that we're in. For the rest of the talk, I'll go for a moment over the forward model just to show you what the acoustic gravity wave equations look like. Then I'll talk about the inference and prediction model and the algorithms that we came up with, as well as some of the computational results, an application of this technology then to the scale of the Cascadia subduction zone. And if I have time in the end, I also share some preliminary results of follow-on work that we have done since then. Now, to start with, the acoustic gravity model, it's a linear model that is posed here as a mixed formulation. If you're interested in the derivation, I'll point you towards the paper from 2015 shown here. So we have the pressure and velocity unknowns. P is the scalar valued pressure. U is the vector valued velocity unknown. And if you're not familiar with this model, one thing that's interesting is this coupling on the sea surface boundaries. So there's an ODE type boundary condition that couples pressure and normal velocity components to a new unknown that's called or denoted by eta here. So eta is the sea surface wave height. So this is added to the model. And then the model itself, the input parameters to the model are the seafloor velocities. And this is what, like I already mentioned in the English problem, what we'll infer. So the boundary forcing here, the model is driven through imposing normal velocities on the seafloor. On the outside of the domain, on the lateral boundaries, there's some observing boundary conditions. And I'll show formulations with the first order impedance type boundary condition, but you can also use PMLs or other more sophisticated methods here. For that, we'll solve the finite element formulation. In this case here, I'll be using a conforming discretization with finite elements where the pressure is going to be in H1, the velocity unknowns in L2, the components. The formulation is shown here just for completeness sake. I won't go into much detail here. Once this is discretized, and we'll be using explicit time stepping here, we have two operators, the mass matrix and the stiffness matrix, that are shown here. Each one of these has some volume integrals associated with this mixed formulation. And then there's a couple of boundary integrals on the sea surface and on the lateral boundaries that also enter the problem here. And then, of course, the load on the right-hand side in our case is this boundary forcing that drives the acoustic gravity equation and generates the acoustic waves in the ocean. So that's the overall forward model. Now, when we discretize this for Cascadia, we'll have to mesh the bathymetry. And before I explain something here, just to give you a sense of the scale, this is a bit zoomed in here. So sort of when you look from above, then what you get is I'm just showing you a little patch of the mesh here. And the scale here is vertically exaggerated. So if you look at the axes here, you have latitude and longitude, and then depth in kilometers, as you see the shelf on the right, and then the deeper ocean on the left. And as you can imagine, when you mesh this, you want to be able to capture these bathymetric features because they will influence both the propagation of the acoustic waves, but also the propagation of the surface gravity or tsunami wave. Now, we've worked with Alice's group in San Diego at Scripps to be able to use forward models or drive our forward models with realistic earthquake scenarios for Cascadia. We don't have any real data for Cascadia. Like I said, the last big earthquake here happened in 1700. So there's a number of different rupture models, and this rupture model is from a dynamic rupture simulation, a high fidelity 3D code that here you're seeing on the left for a margin-wide rupture of Cascadia, magnitude 8.7 earthquake, the vertical displacement field, and then on the right, the normal seafloor velocity field. And the time, as you see, propagates, the rupture propagates north and south. It takes about 2 minutes to fully propagate. So this is a very complex and long earthquake event here for a margin-wide rupture scenario. There's also many partial rupture scenarios that we've looked at. And in a sense, when you think about the inverse problem, the field on the right here is what drives the problem, and that's what we want to infer in the inverse problem. And you can see there's a lot of high frequency components in here, spatially and also in time. So as an example here for this margin-wide rupture scenario, the forward model, let me also pull up a video here. I don't have a 3D visualization just because of the amount of data that this would write out. This mesh has many billions of degrees of freedom, but I'll show you two different plots. On the left, the sea bottom pressure, and then on the right, the sea surface wave heights. So the left plot corresponds to what you would be observing if you placed pressure sensors in the domain. And then the right is basically what we are interested in forecasting in real time, which is the surface wave heights. So on the left here, high frequency acoustic fields. On the right, you can see both the higher frequency field from the ground shaking, but also the vertical column that's being uplifted, the water column, which is sort of like this big red blob that's being uplifted here, that will then propagate as a tsunami toward shore. Of course, all of this is happening here on a timeline where we are really interested in the acoustic fields and the generation of the tsunami wave. Now, if you are interested in tsunami propagation all the way to shore, then you'll probably take larger time steps and then also propagate it all the way to the coastline. But here in the inference problem, we're really interested to see what's happening in the area of the subduction zone where the ground is moving the most. Okay, so this is the forward model. And now I'll get to the inversion and prediction model. Now, I've said it many times already, but just to state it one more time concisely. So we assume that we are given pressure recordings from sensors located on the seafloor. And from that, we infer the seafloor motion, the velocities of the seafloor in the subduction zone. Once done, we have a forecasting problem, and this is where the goal-oriented component comes in of this digital twin that I mentioned in the title. Given the inferred spatiotemporal seafloor motion, we want to forward predict the tsunami wave heights at specified coastal locations, and all of this we want to do under uncertainty and with high fidelity PDE models. Just to set the stage with a few, the way I'm going to denote the different quantities here. For the parameters that we seek to infer, I'll use M. This is, again, the seafloor motion or the velocity field in this case. The data, the observables, I'll denote by D. So those are sparse but pointwise pressure observations on the seafloor. And then we have this mapping from parameters to data. So given a parameter field or a discretized parameter field, the parameter-to-observable map will take this parameter field, solve the forward PDE model given this parameter field as a boundary forcing, and then apply an observation operator that extracts the observables at the sensor locations, which in our case is only the pressure unknowns. Of course, this problem, if you're familiar with inverse problems, it's a very ill-posed problem for many reasons. One of them is that we have a very underdetermined system. We have this giant parameter field, but we're going to have sparse data. And the way Bayesian inference addresses this ill-posedness is by not describing just a best point estimate of the solution, but rather characterizing the solution of the inverse problem as a posterior distribution so that we can get an uncertainty associated with whatever best prediction we come up with. And base rule here, just abstractly given the posterior of the parameter field here is proportional then to the prior times the likelihood of the data conditioned on the parameter field. And we'll be using a Gaussian setting because that will leave us with a linear inverse problem. You'll notice here, and this is going to be an important fact, the PDE model itself is linear and the parameters enter this PDE model in a linear way. And the observation operator itself is linear, right? It's just observations of the pressure field. So this P2O map, the parameter-observable map itself, remains linear. It's very large scale, very expensive to compute, but it's still a linear mapping. And that will be important. Now we'll use a Gaussian prior with a Matern type covariance operator as shown here. That's an inverse elliptic operator that's discretized and applied. And for the likelihood, we assume also Gaussian additive noise. And if we do this, given the linearity of the P2O map and the Gaussianity assumption for noise and prior, we can write down the posterior in a closed form solution. The posterior itself becomes a Gaussian. This Gaussian is centered at what we call the map point, the maximum a posteriori point, and has a posterior covariance that can be explicitly written down as shown here. And I want to just point out a couple things here. So first of all, this posterior covariance, which I also refer to it as the inverse of the Hessian operator, in our case, it's going to be a gigantic dense matrix. So the Hessian here will be of the order of 10 to the 9 times 10 to the 9, a dense operator. So something that you cannot pre-compute and store, obviously. It would be on the size of exabytes to store this. Each application of this operator in a matrix-free way, each action of this operator on a vector will necessitate the application of F and F star. So that's a forward PDE solve and an adjoint PDE solve, each of which are large-scale PDE problems to compute, so very expensive. And then lastly, just to solve the best point estimate here, the map problem, the map point, we'll have to solve one of these problems with the posterior covariance. And this doesn't even talk about characterizing this operator itself. And I'll get to the kind of how much time this would need with conventional methods. One interesting quirk to also point out, because we're in the linear setting here, is that you'll see the observables, the data show up down here on the computation of the map point, but in fact, the uncertainties themselves, the covariance itself, is not dependent upon the data. And that might be a little counterintuitive, but this is just what happens in a linear inverse problem. And so the uncertainties will be characterized or coming really from the PDE model, from the central locations, the bathymetry, all of those things, but they're independent of what the actual observations look like. Of course, there's an assumption on characterizing the noise covariance. Now, in the goal-oriented setting, I'm additionally quantifying a quantity of interest, the QOIQ, the surface wave height predictions, and there's a similar mapping from parameters to QI. So given real-time data, we can predict the QI, and in this linear setting again, these are Gaussians, the posterior here that is just pushed forward through the parameter field, and the posterior of the parameter field. Now, the usual approach for solving this, as I mentioned, these Hessians that we have to apply to solve the map point problem can be applied in a matrix-free way that necessitates the forward and adjoint PDE solves per Hessian action. And this is something that can be done at large scale. has been done for a number of different inverse problems that are very large scale. And often, one technique that works well in many cases is a low-rank decomposition of the Hessian of the data misfit. And this can sort of like make the computations tractable. As you will see in our case, this is a technique that won't apply here because we have in fact a very high rank Hessian due to the hyperbolic nature of the problem. Now, the challenge here, like I mentioned, the Hessian has high rank. And in the Tsunami problem, what this means is the parameter field, as we'll see, is discretized about 1 billion parameters. The data dimension in our case, assuming a few hundred sensors, is on the order of 10 to the 5 against spatiotemporal data dimension. And we'll see that the rank of the Hessian is, or the effective rank of the Hessian is nearly full, so about 10 to the 5. So you would need, for a CG solver preconditioned by the prior, you would need about 10 to the 5 iterations to just solve the map point. And assuming 1 hour per Hessian action, which involves the forward and adjoint PDE solve, and this is still an optimistic estimate for a large GPU cluster given the problem size, you would need over 10 years just to find the map point. So this isn't just not feasible in real time. Forget about real time. It's really infeasible to do this at all. Using a supercomputer for 10 years just to find this one inverse problem solution, not even having characterized the uncertainties yet. The traditional fix for problems like this would maybe be using reduced order models, maybe some surrogate neural networks. But those also are extremely challenging here. It's because we have a ginormous parameter dimension, like I mentioned. Furthermore, in this hyperbolic setting, at least for linear subspace representations, there's something called the Kolmogorov-N-width barrier, which shows that the best approximation error decays slowly. So small subspaces are really not a good, effective way of characterizing solutions. Here's just to drive the point home. The eigenvalues of the prior preconditioned Hessian, or the inside out one of the data dimension. This isn't for the full Cascadia problem, but so like a smaller patch, but still a large problem. And you can see that the eigenvalues decay very slowly, even for the preconditioned operator. And so maybe you can justify saying, okay, it's fine to forget about the modes associated with the really small eigenvalues back here, but this is a very informative setting. So in a certain way, it's good. It means the data are very informative for the parameter field in the inverse problem, but it also means that we can justify using a low rank approach here. So it really makes the cost of computing the inverse solution prohibitive in the usual way. And it would, like I said, take many years on a supercomputer. So what do we do? We'll be exploiting that a certain structure in the problem, and the structure is called an autonomous dynamical system. And more specifically, in our case, the PDE operator is what we call a time invariant system. Now, in a time invariant system, which is sort of abstractly written down here, we have a PDE operator A that is time invariant itself, and then C, which moves parameters into the problem, and B, the observation operator, also time invariant operators. And from a just philosophical point of view, if you think about it, if the parameters at a time, at a given time, how they influence the data, the observations, if you shift this in time, the relation between parameters and data doesn't change. And this is the time invariance we're talking about. Now, if you discretize this, and this works for any really spatial discretization method and different time stepping methods, but it's shown here for a simple time stepping, you'll find that written down in discretized form, you get the structure in the problem, where the discretized operators appear and are kind of repeating diagonally. So these are block operators corresponding to the time stepping. Each of these block operators is very large, spatially speaking. Spatial parameter field has 1 million parameters, and then the whole thing is 10 to the 5 by 10 to the 9. And we can identify these sort of, I guess, these subblocks of the parameter-to-observable map. And this type of matrix that you see here, we call it a block triplet system. Why is this important? It's important because this block triplet system has the properties that we can exploit very effectively. So first of all, clearly, if you wanted to pre-compute this map and store it, you could do it just by pre-computing this first block column. You don't need to compute all of the columns because the operators are time shift invariant, as you see here. And more importantly, what this means is that in order to pre-compute this entire operator, the number of computations we need to do, the number of applications of this operator we need to do is only as many as there is number of physical sensor locations in our problem, the spatial locations of sensors. So by doing as many solves, adjoint solves, which correspond to the last block column of the adjoint operator, F star, we can compute this operator. It's fairly compact then to store it, just the first block column. And then on top of that, because it's a block triplets matrix, we can embed the block triplets matrix into a block circlet matrix. A block circlet matrix is diagonalized by the Fourier transform. And so we have a very effective, efficient way of computing matrix of this operator for the forward and adjoint in Fourier space, which will, once pre-computed, avoid doing PDE solves altogether and compute a block diagonalized operator, which it will turn out is extremely fast. Now, in order to solve the problem, what we came up with is this four-phase framework then. I'll go through each step in just a moment here. So in the first phase, we'll pre-compute these operators. We have to do as many solves as there are spatial locations for sensors and quantities of interest points that we want to predict. So this is on the order of a few hundred, but these are expensive, but it's doable. This is all offline. There's an offline-online decomposition here. Then in phases 2 and 3, there's a number of different computations that happen offline. And then the online phase is where we compute the parameter and QI map points in real time. And together with the uncertainties that we pre-computed, we can then specify as the inverse solution in real time, as you will see. And importantly, here I want to point out, there's no surrogates or reduced order models necessary, in fact. So we are going to be able to compute this inverse problem exactly with the high fidelity model in a matter of seconds. So for the computation of the PDE problem, this is where really the first supercomputing component came in. So we had access to a number of large machines, El Capitan being the largest one, #1 supercomputer, which it still is as of November 2025. And the recent top 500 list even has more GPU chips now. So we had access to this. We also ran our PDE model on Alps and Perlmutter and did a great number of optimizations here for this model. I skipped the scalability setup. Like I mentioned, this is very large scale, of course. So part of the Gordon Bell paper is to show scalability and being able to go to very large problem sizes. Now, strong scalability, we have a fixed problem size. We increase the number of GPUs that we use, in this case, going for El Capitan, the biggest machine here, from 340 GPUs all the way to the full machine, 43,520. And we get extremely good strong scaling for all of these machines here. At the full scale El Capitan, we had about 79% parallel efficiency, which meant for a problem with about 400 billion degrees of freedom, we're able to take 100,000 time steps in just about 5 minutes on the full machine. Weak scaling is where we fix the problem size per GPU, and then we make the problem larger as we make the number of, as we take more and more GPUs. And so this plot is shown here. And again, for El Capitan, the biggest machine going to full machine size, we get about 92% parallel efficiencies. And here we're able to solve what we think is the biggest unstructured mesh finite element solve that has been reported. So the total number of degrees of freedom here was about 55 trillion, which comes down to about 1.28 billion degrees of freedom per GPU. And for this, most of the machine memory we used was about 5 petabytes of memory on the machine that we had to use for this. So clearly we have a scalable solver, but we also already discussed that a scalable solver alone won't do it. So we'll have pre-computed this parameter-observable map, but one issue that remains is that the forward and adjoint of the parameter-observable map, while we have those, we don't have the Hessian yet. And the problem is that formulating the inverse Hessian is this 10 to the 9 problem for the parameter space. So what we recognize, though, is that the data space dimension is much, much smaller. And so what we'll do is we apply the Sherman-Morrison-Woodbury formula, which reformulates the Hessian from the parameter space to a problem where the inverse operator here is applied to a matrix of the size of the data space, which in our case is not 10 to the 9, but on the order of 10 to the 5. So this comes at a cost of applying these operators on the outside of the problem here. But really, the inverse operator is shifted to a much smaller matrix. So K is a dense matrix. It's 10 to the 5 times 10 to the 5, and we can for this matrix size, actually compute, for example, a Cholesky decomposition that's feasible. So all we need to do is pre-compute this matrix K, which involves 10 to the 5 forward and adjoint PDE solves. Not something we could have done with the PDE solver, but with the FFT-based solver, as you will see, this is not going to be a problem because we can do really rapid F and F star evaluations. There's a couple of other tricks that we apply here, but none of them make any approximations. In the third phase, again, quantifying uncertainties is difficult in the parameter field. Like I said, the Hessian is 10 to the 9, the posterior covariance is 10 to the 9, that's 10 to the 9. Even with an effective solver, 10 to the 9 matrix actions turns out is too much. But what we are able to do is something on the order of 10 to the 5 or 10 to the 6 matrix actions. So we're able to quantify uncertainties for once in the time integrated parameter field, which is the seafloor displacement at the end of the time we're predicting for. And then we can also quantify uncertainties in the goal-oriented setting. As I mentioned earlier, what we really are interested in at the end of the day is these tsunami wave height forecasts. And in the goal-oriented setting, this posterior covariance can be pre-computed through the operator shown here. The P to Q map, the parameter to QI map, has the same structure as the P to O map. So we can play the same block triplets trick again using the FFT-based solver, and then pre-compute this entire operator here. All of these computations can be done offline ahead of time before any earthquake occurs. And in fact, for the Q, if we are only interested in the QI, so if we do a purely goal-oriented approach and say, okay, we don't actually care about the seafloor motion, we just want tsunami forecasts, we could in fact pre-compute the mapping from data to inference to QIs, which becomes a dense matrix that maps directly from the observations to the QI, which in our case, if you just assume some offshore locations that you want to forecast for early warning, this could be as small as an 8 GB stored matrix that of course is expensive to pre-compute, but once pre-computed can be applied to observations in a matter of seconds on just a laptop. The online computation reduces to characterizing the map point and the QI point, applying the parameter QI map, and then these various operators up here. So these still involve, as you see, the parameter-observable map. We have to invert this K map, which we can, again, Cholesky decompose ahead of time. G here is a composition of the prior applied to the parameter-observable map, which itself is also block triplets where we can solve with the FFT solver. And the important fact is none of this requires a PDE solution at the time of inference. We have a mapping from data to parameters that sort of happens without having to go through the PDE pipeline because we are avoiding this by having pre-computed the entire operator. Now, applying this to the Cascadia subduction zone for a large scale, like I mentioned, the parameter dimension here is about 1 billion. 250,000 is the data dimension. The state dimension in this case, spatial degrees of freedom, is 3.7 billion or so. And here we're assuming 600 sensors. And to just go through the pipeline one more time here in a sort of like visual way. So we have this 4-phase framework, and in phase 1, we have these pre-computations of these P2O and P2Q maps, doing as many PDE solutions as there are sensors and forecasting locations. For this, we have to use the PDE solver. So this is the MFEM-based solver, this very scalable solver I was showing earlier. All the rest of the computations are going to be using a custom solver, which we call FFT-MATVEC, and a custom inversion algorithm based on that. And there's 2 phases that are still happening entirely offline that make use of the solver. And then the online phase in the end is given the observations we infer the parameters and predict the QI. As you will see, we can do this in real time. Here's the computation times for the Cascadia problem size. So we had to use 500 GPUs here to do the PDE problems. Each PDE solve takes about 50 minutes on 500 GPUs. We had to do 600 of those. Those don't have to be done one at a time. They can be all done at the same time, depending on how many GPUs you have access to, but it takes some considerable time. This is the most expensive part of our framework, this phase 1. The other computations in phase 2 and 3, which apply these operators F and FQ many times, in this case down here, 250,000 times, you can see just how fast the FFT solver is. It takes milliseconds to apply these operators. So this is all done in the order of minutes. So the FFT solver is incredibly fast in applying these parameter-to-observable maps, or their adjoints. The actual inference of the parameters and the prediction of the QIs can be done in real time given the data. And here we were able to show that using the same number of GPUs, we can solve the entire inverse problem in 0.2 seconds, which, in comparison to if we computed this the traditional way for the map point, would take, like I said earlier, more than 10 years of computing time. So what we came out with was roughly a 10 billion fold speed up if you just look at the inference of the parameter field. So this is the real-time aspect. Now let's look at some results for the Cascadia case. Here is the inference of the parameter field. I'm going to be showing it as normal displacement instead of velocity, because it's a bit more informative to look at this. On the left is the ground truth of the normal seafloor displacement. On the right is what's inferred in real time. And you can see that we do a fairly good job characterizing the smooth components of the inverse solution. And if you're a problem working if you have worked in inverse problems before on this community, then you probably look at this solution, you say, okay, well, job well done, let's go home. If you are not, then you might be wondering, well, what's going on with all these fine scale features here? They don't seem to be captured. Well, this is just fundamentally the case of an ill-posed inverse problem. We're not going to be able to recover from sparse data these finer features that are sort of in the noise. So all we can hope for is recovering the smooth components of the inverse field as is shown here. And for that, we're doing a fairly good job. I'll show you in a little bit later the error that we get in the displacement field in the inference. But yeah, like I said, the smooth components are inferred quite well. And that's important, as we'll see, for the QI forecasts. Here, just before I get there, you see the 600 sensor locations. Again, you have to also consider the domain size. It's more than 1,000 kilometers long. So those sensors are actually spaced apart by something like 25 to 30 kilometers, I believe, is roughly the spacing of the sensors. On the right here is the uncertainty field for the displacements that are computed, shown as pointwise standard deviations. And you can kind of see both the sensor structure in here, but you can also see that in the shallower parts of the domain, there's less uncertainty compared to the deeper parts of the domain. On the boundary, the uncertainty that's higher comes just from the fact that there are fewer observations, and the mesh has an absorbing boundary, so there's no information back propagating. So that means there's less certainty about inference there. But yeah, so that is something we can, like I said, pre-compute. For the QI forecast, the Tsunami wave heights, you see results here. We selected 21 points to look at, which we computed those real-time predictions for. And you can see the true QIs here and the predicted ones, and then overlaid with 95% credible intervals for these computations. And you can see that even though we weren't able to infer these smooth, the higher frequency components of the displacement field and the parameter field, those don't seem to be the ones that account for the surface gravity of tsunami formation. It really is the lower frequency components, and those we recover really well. As you can see here, we get a good recovery of the tsunami wave heights. Okay, with that, I think I have maybe about 5 minutes left or so. So I just want to use the last 5 minutes to show some preliminary results here that we have worked on some follow-on work since then. So one is the results I've shown you so far. As a ground truth, we have used dynamic rupture earthquake models. Those were elastic solid earth models where the seismic waves are propagated. Alice's group also has fully coupled models that couple the elastic solid to the compressible ocean domain. So that it accounts for the elastic, the acoustic, and the tsunami. So those are forward models. And what we wanted to do here is we want to cross-validate our acoustic gravity forward model with these fully coupled models. But then secondly, also instead of using these elastic-only dynamic rupture models, use the fully coupled ones, which can have a more complicated seafloor ground motion because of the coupling between the solid and the water layer So the interface waves that propagate there are captured in this model. And then finally, we also wanted to use a network of only 175 sensors here, which you'll see is something much more realistic to assume based on sensor networks that have been installed elsewhere. First, we did a cross-validation of the forward models, and you can see here for the tsunami wave heights, we actually get very nice correspondence between these two models. They're implemented in completely different codes. The fully coupled model in Sisal using a technique called ADER-DG, discontinuous good looking, and then our MFEM implementation. And you can see a very nice correspondence between the tsunami wave heights for these QI points. For the inference, again, these are preliminary results. I haven't rendered a video here yet, but you see similar results for the normal displacement field. Looking at the relative errors, the displacement field here has about 35% error, the one that is inferred from the 175 sensors. This is about 5% or 6% more than with the 600 sensors, and the QI forecasts have about 3 or 4% more error. So we have about a 21.5% error in these forecasts. And then finally, also preliminary results, we have worked toward implementing a digital twin framework of this kind for the Japan Trench. So completely different subduction zone across the ocean, across the Pacific on the other side of the planet. And of course, most of you are familiar with the last, or all of you are familiar with the last big earthquake that happened here in 2011, the magnitude 9.0 Tohoku earthquake, which caused tremendous damage and loss of life in Japan. And of course, also the Fukushima nuclear reactor disaster that happened at the same time due to the tsunami wave hitting the shore. And so this is a subduction zone that's of particular interest. For this, we also have dynamic rupture models from ALICE, and those rupture models are like best estimations of the Tohoku earthquake. And I want to show these because we'll see some differences compared to before. Again, on the left is the vertical displacement field. On the right is the seafloor normal velocity. And the Japan Trench is very deep and has very different features from Cascadia. So when you look at the seafloor velocity field, you can see it's much, has many more higher spatial frequencies than what we had in Cascadia, including when you look at the vertical displacement field here, it just has much sharper edges. So that's going to make the inference problem somewhat more tricky, recovering this correctly and accounting for the tsunami formation. So this is something we've looked at. We're not done with the computations yet. But why is this of big interest? It's because Japan has already, following the 2011 earthquake, installed large-scale sensor networks of the kind that we have based our digital twin assumptions on. And one example of that is this huge sensor network called SNet, which is connecting through 5,800 kilometers roughly of fiber optic cable laid on the seafloor. It's connecting 150 observation stations that are on the seafloor, which each have seismometers and pressure gauges installed. And so those can be used for real-time earthquake and tsunami early warning. Here you see those locations just mapped on the bathymetry plot. You can see they actually go across the Japan Trench onto the other side. One thing that makes computations quite tricky here as compared to Cascadia is just this bathymetry. So when you think about the Japan Trench, it's much, much deeper than the Cascadia subduction zone. It goes down to more than 8 kilometers depths. It's also what's causing these velocity fields that you saw to be very complex in comparison to our earlier scenarios. And capturing this area here it turns out to be like quite a bit larger even than Cascadia in terms of meshing. And because the ratio between the deepest part of the ocean and the shallowest part of the ocean, which is less than 100 meters deep, what we're capturing here where the sensor locations are, is very high, this ratio. We need sort of like anisotropic adaptively refined meshes, which we used. They generated an MFEM on the fly on a parallel partitioned mesh. Even with those anisotropically refined meshes, we still have quite a few more degrees of freedom. I think this mesh had about 10 billion degrees of freedom for Japan. And here's just one last video I'll show of the forward solution. And again, on the left, like earlier, the sea bottom pressure field, and on the right, the sea surface wave height that forms. And again, this is what, had the SNet been in place at the time of this earthquake, it would have seen pressure wave corresponding to this, assuming that our dynamic rupture model is a good representation of the actual earthquake that happened. And then the sea surface wave heights here on the right, and this is something we're in the process of doing now, is looking at these forward models and cross-validating them against some historical data of tsunami wave heights that have been observed by some pressure gauges that were already installed at the time when this earthquake happened. Okay, so let me wrap it up here, and thank you for your attention. There's a lot of ongoing and future work I'm happy to talk about. The big takeaway here is that we were able to solve this large scale inverse problem really in a fraction of a second. And while you ask me questions if you'd like to, I'll leave you just with this last video that we had submitted for the Art of HPC, which is sort of like an annual thing at supercomputing now. It's sort of like an artistic rendering of our earthquake event that overlays some different components of it, both the seismic waves and the tsunami waves. So you can see sort of like the Pacific Northwest coast here in the background. And then this was a feature for some computations done on Capitan, this large computer in Livermore. So with that, let me end it here, and thank you for your attention.
Thanks. Yeah, that was great. Normally we would clap. Maybe I'll do the virtual clapping here. Oh, thank you for doing that. Are there any questions for Stefan? Let me open up the chat too. Oh, you're getting a lot of clapping here, a lot of virtual clapping.
So I can, oh yeah, go ahead.
This is Kumar Vimaganti from Sandia Labs. Very nice work, Stefan. I was really happy to see your results, and also as an alumnus of the Odin Institute, it's always nice to see work by a fellow Longhorn. So one question I have for you is about the choice of the priors and things like that. But I'll reach out to you offline about that. But one question for now is, how do you differentiate between a digital twin and a computational model, right? What makes this a digital twin rather than a model?
I think everybody has probably their own definition of what a digital twin looks like. But for me personally, the way I see it is that the reason why I would call this a digital twin is because there's two reasons maybe I should mention. But the most important one really is that there's this two-way flow of information, if you will. So we have a physical system that's represented virtually as a digital model, but then we don't just take observations that are happening in real time and build them into the model. So, this data assimilation component, but we are using then this model to inform things. And this could be, a digital twin could be control. So, using the inferred parameters of predicted QIs to control a system. In this case, we don't have control because it's the Earth system that's moving here. But we have the two-way flow of information in the sense of being able to use the forecasts and the inference here to inform decision-making. In this case, decision-making about early evacuations. And as the physical system evolves, we can continuously update the forecasts. This is also just a characterization of a digital twin. On top of that is, this uncertainties are just something that I think are essential in this context, because really for either one, control or decision-making, uncertainties kind of is really crucial, because we need to be able to confidently say whether a forecast is the tsunami wave height going to be in this bucket of like a 50 centimeter estimate, or do we have an uncertainty of 2 or 3 meters? So based on that, of course, that goes into the decision-making process as well. And then the real-time component, that kind of comes from the necessity of control and decision-making. So that would be my take on that. And I'm sure other people might have other views of it.
Okay. Thank you. I appreciate that. Thanks
for the question.
Yeah, it's a great question. This is always an important semantics things with buzzwords like digital twins. Other questions? So I can ask one, and I don't know. It's actually about the prior. So I don't know, Kumar, if this is what you had the question on too. But so you're using this normal prior assumption and kind of like this linear Laplace approximation to enable some of these analyses, which is, I think, one of the reasons you're able to kind of get the cost savings you do. But is it possible to do this analysis given how many parameters there are with just a generic or not generic but a non-Gaussian prior? Or have you guys thought about that? Or I mean, maybe the Gaussian prior is a reasonable thing to do, and kind of that's where you're leaving it at. But I was just
Yeah,
curious.
no, it's a great question, and it's something we've thought about for sure. Here, I will say that the Gaussianity assumption is essential to being able to do this offline-online decomposition. If we go to a non-Gaussian prior, we don't have a linear inverse problem anymore, so we can't decompose the solution the way we've done here, which is really kind of crucial for being able to solve this inverse problem in real time, being able to do those pre-computations. But having said that, this like elliptic differential operator that we use as a prior here, that is a smoothing operator at the end of the day, really was just kind of a generic choice in the sense that we know it works, and in the absence of any better knowledge, we'll take that. Because a certain smoothing is always likely, like when you think about spatial parameter points or seafloor points being close to each other, they're probably not going to move in very different directions, or there's going to be some time correlation as well. However, we have looked at constructing data-driven priors for Cascadia, and I'm not sure if Bowen is online, but one of the PhD students of Omar is actively working on this. So there are a number of rupture scenarios. There are databases of rupture scenarios. There are, assumed to be realistic or hypothesized ruptures. There are, different people have worked on this, and there's one database of 1,300 such rupture scenarios. So we have some idea of how the faults could rupture during an event, and not all of them are these margin-wide ruptures. Most of them are just partial rupture scenarios. And using those data sets, we can actually construct seafloor motion data sets, which then can be used for the inference. So that means constructing a prior that incorporates information about what an earthquake actually looks like and what ruptures would be likely looking like. But still, even in that case, going to an entirely non-Gaussian prior. So at the end of the day, you're probably going to have to Gaussianize again if you want to stick with the same framework. Otherwise, you're going to have to come up with something else here, because the decomposition in offline-online isn't going to work. So even in that case, you probably want to build this into a Gaussian prior of some kind, but incorporating that information is probably something that should be done, given that we have that prior information available.
Yeah, that makes sense. I guess my other question, well, you kind of answered it just now, but I was curious if you've looked at data-driven surrogates. I mean, not within this approach because it doesn't need a surrogate, but just in general for this problem as an alternate approach. It sounds like you do have a student who's looking at that, and maybe like a multi-fidelity type of an analysis would be viable here, where you're not solely relying on the data-driven model, but you have kind of a mix of models, and you're only sampling the higher fidelity one a few number of times.
Yeah, I think one place where I can really see a surrogate coming in, and we have another student working on this as well, is when it comes to doing inundation forecasts. So right now we're doing offshore locations tsunami forecasts, and that's something that NOAA uses, in fact, for guiding evacuation decisions. Those, they also have models doing prediction of offshore points here in Cascadia. But if we want to also do real-time predictions of inundation, then that would require solving a nonlinear model. So this acoustic-gravity PDE model is not a good approximation when we go into very shallow water. There you would be able to take the solution we infer and then forward propagate it, say, with a nonlinear shallow water equation solver. That solver itself is something we couldn't solve in real time either. The PDE model would be too expensive for real-time computation. And this is really, I think, where surrogate modeling could play a role in terms of doing those types of inundation forecasts.
Yeah. So Naomi Petra, it looks like she has a question. So do you want to just unmute and Naomi and ask?
Hi guys. Hi Stefan. Excellent talk. Thank you very much. I finally understand what's going on here. So thank you so much for all this insight. I have a question. I'm wondering if in these models, do you guys have any additional uncertainty in terms of, you invert for, I don't remember exactly the quantity for M, but I assume there are other uncertainties as well. And I'm wondering if you have given any thought in terms of how to account for those additional uncertainties into your Bayesian inference.
Yeah, so
what I'm asking?
oh, sorry. Sorry,
Do
go
you
ahead.
understand? Is that my question?
No, it makes sense totally.
Okay,
Yeah, right now I think uncertainties, like I said earlier, are really primarily driven by the physics of the model and whatever assumptions we make on the noise and the sensors that acquire the data. And in fact, we're using a diagonal noise covariance here, and that
Sure.
makes those pre-computations, much more feasible than using some other noise covariance operator.
Sure.
Now, I think incorporating uncertainty in terms of like the model uncertainty itself would also be something we could think about.
Yeah,
And
but other parameters, for instance,
Mhm.
I don't know, there is a lot of uncertainty, I assume, in the geometry, maybe on the right-hand side, other things, right, that could be uncertain as well. Or is that not as important as the one that you chose to invert for?
Right now the biggest one is the one that we are using right now. That's the one that kind of was the natural one to start with. But yeah, I agree. I mean, there's other types of uncertainties. There's some uncertainty even about, the discretization of the bathymetry. I mean, we have a fairly good idea of what the ocean floor looks like, but we don't necessarily always have exact data. In the way that data is being acquired, the additive noise Gaussian assumption is something that is not necessarily, a true assumption either. So yeah, I think building in uncertainties into other parts of the, the inversion pipeline would be good to do, but it is difficult to do it in the context of being able to pre-compute these operators because, like I mentioned earlier, you have to solve the inverse problem essentially 250,000 times here to construct the operator. And so anything you do within this inversion pipeline would have to, still fit into that framework. So yes, you could think about including other types of uncertainties, but I don't see a clear way of doing it unless it fits that framework. And then again, there's clearly an assumption. So I think maybe combining different types of inference models here is a better idea. Like use this high fidelity model that captures the high fidelity physics to do one this type of inference, but you can probably complement it with simpler. I mean, the current approaches that are out there are probably incorporating other types of uncertainties as well, but they're very crude from a modeling point of view. They don't solve any acoustic gravity wave equations. They don't solve any PDE model at the time of the inference at all. But they probably can do some of the things that you're thinking of. Yeah.
Sure. All right. Thank you so much. And
Thanks for the
congrats
question.
again for this amazing award and work. Thanks.
So I think we're over time, so we do have to end. And yeah, thank you, Stefan. This was really great. And yes, congratulations on the prize.